All right, class. Today we're going to add to our understanding of the concept of equilibrium. Um, on Monday, you guys learned about kind of what equilibrium is. We did the water demonstration in class. Um, the first video talked about how equilibrium dealt with the rates. You have two reactions, a forward and a reverse reaction. And what's important is that the rates eventually end up equaling each other. And we talked about that in the first video, how that goes down. And then we talked about equilibrium constants, kind of how we can tell what's being favored. Is it a forward reaction favored, or is a reverse reaction favored? What we're going to deal with now, and especially since we're answering the question, how far will a reaction go? When you have a reversible process, like a reaction that's reversible, one of the problems we face is once that reaction reaches equilibrium, really nothing new is produced. The reaction does keep going, but if you remember in the water demonstration, once you reach that point of equilibrium and you're transferring the water, you reach a point where the water level doesn't change in each bucket because you're transferring the same rate throughout that time period. Same kind of thing here with a chemical reaction. So what we use in kind of practical science, and a lot of machines and factories are built on this principle that deal anything with chemistry, is how to manipulate a reaction. And what are some tools that we do? And since, remember, we're talking about rates here, so a lot of this is going to kind of connect back to previous chapters where we dealt with rates. Now, some of it will be a little different, but to a large extent, we're going to connect back to things that affect and influence rates. So the first thing we're going to deal with, and basically what we're going to talk about today, is Le Chatelier's principle. And what it says, and you will need to know this definition, so this is key, that when a reversible process is disturbed, it will proceed in the direction that relieves the most stress. Now, at face value, that definition, without explaining it and kind of visually seeing what's going on here, you may be kind of scratching your head. Reversible process, we're just talking about a reversible reaction. A reaction that can go forwards, so reactants producing products, and it can also go in reverse, which means products can break down and produce reactants. So that's what we mean by reversible process. What we're saying is that once it reaches equilibrium, then those rates are equal. But if we disturb that equilibrium, okay, then it's going to proceed in the direction, in other words, it'll either proceed forward or it'll proceed in reverse, depending which direction relieves the most stress. So we're going to talk about a couple things that we can do to manipulate a reaction and how you would be able to predict what direction it would go. And that's kind of what I would ask you on the test, is I might give you a scenario. Here's a reaction and here's a scenario. Here's what we're doing to it. Which direction would that push the reaction? So you're going to kind of need to pay attention here. This is going to be the sample equation that we're going to use, chemical equation. Here's our reaction. We have sulfur dioxide plus oxygen gas, and it's going to yield sulfur trioxide. Okay, so that's our chemical reaction there. And the first factor that we're going to deal with three. But the first one we're going to deal with that can disturb equilibrium is concentration. Remember that concentration deals with amount. Okay, so what we're saying here basically is this. If you remember, we start off our reaction with a whole bunch of reactants and no products. So initially you have a high concentration of reactants and no concentration of products. But once you reach equilibrium, you have something in between there. We don't know what it is, maybe 30% reactants and maybe 70% products. Who knows? Okay, it could vary from reaction to reaction. The point is this. What happens is the rate of the forward reaction has been decreasing because you're using up your reactants and they're becoming products. They're bonding together and becoming products. And so you have more products and fewer reactants, so there's fewer collisions. So your rate there slows down. Your rate of your products breaking apart and becoming reactants speeds up, and eventually they reach that equilibrium. How can I disturb that? Well, when I'm dealing with concentration, I'm dealing with changing an amount. So one thing I could do is I can change the amount of a reactant or both reactants. I could add more of both reactants. Or if you remember a lab we had a while ago where we talked about limiting reactants, okay? So that's the one that runs out first. So let's say that was SO2 in this case, sulfur dioxide. In that case, let's say that was my limiting reactant. I run out of that. What can I do? I can add more. I'm increasing the concentration. Well, what will that do? If I increase the concentration of a reactant, I'm going to now have more collisions because I have more of them. So I have more collisions of reactants. So what direction is that going to push the reaction? It's going to push it forward. Okay, because what are those reactants going to produce? Products. Okay, and the opposite is true. What if I added more product? Okay, well then I'd have more collisions there, so that would again change the rate, so it would force it in the reverse direction. Make sure you understand which direction it would force it. Also, okay, another key concept here and something to understand is I can also, instead of adding concentration, so increasing my concentration, I can decrease my concentration, which is actually what we do a lot of times in factories. You take something and you produce whatever it is. Okay, so let's say we want to produce sulfur or trioxide here. That's our product, and that's what we want to produce. Well, what would you do to keep the reaction? You remove it. Okay, and if I remove it, then what it does is it changes the rate of, there's now fewer collisions on the product side. Why? Okay, because there's less of them, so it slows that rate down. So what happens? The forward rate is still the same, so it favors, okay, the forward reaction, so it's going to push it in the forward direction. The same will be true if I removed a reactant, then it would push it in the reverse direction. More often than not, we actually use a combination of these. So a lot of times in a factory or something like that, to keep the process going so it never reaches equilibrium, you will add more reactants on a regular basis, and you will remove the product as it's formed, so that way you're pushing it in the direction that you want it to go. So that's one way we use concentration. Okay. Continuing on, factors that can disturb equilibrium. We already talked about concentration. Now we're going to talk about pressure. All right, one key thing to remember if you're looking at our chemical equation, when I'm talking about pressure, pressure works a little bit differently. If this is a chemical reaction, even though we write it in an equation and there's separate sides to an equation, with the arrows there in between, it's not that they're actually in separate containers. Okay, the reaction, you mix the reactants together, they react and produce products. It's all together. So let's say we're doing it in a beaker. They're all mixed together. Okay, products and reactants, it's all happening in one spot there. So when I apply pressure, I'm not just applying pressure to just the reactants or just the products. I'm applying pressure to the whole thing. So the question is, if I'm applying pressure to the whole thing, which direction is that going to force it? Okay, a fair question. Well, here's how you do it. It's actually really a simple answer. What you do is you add up the number of moles on each side. And depending which side has the greater amount of moles, it's going to push it in the opposite direction. So I'll show you how this works here. As soon as I get my pen ready. Okay, so on this side here, you have a coefficient of 2. And then over here, our coefficient basically is 1. Okay, and on this side, you have a coefficient of 2. Remember, those are your moles. Okay, your coefficients are your moles. So on the reactant side of the equation here, I have a total of 2 plus 1, so a total of 3 moles. Okay, on the other side, I have only one product, and its coefficient is 2. So I have 2 moles on the product side. So the way I decide which direction, if I put pressure on this equation, what direction is it going to force it? Always forces it from high to low. Okay, so what side's your high side? Okay, that would be the 3. Your low side is the 2. So it's going to go from high towards the low. Okay, and so once we know that, well, what direction is that? Well, it's flowing from reactants towards products, so that would be a forward reaction. So in this particular reaction, if I applied pressure, it would push it forward. Okay, now if it was the opposite, if 3 was on the product side and the 2 was on the reactant side, then it would force it in reverse. Now, here's an interesting one. What if you end up with a chemical equation, and sometimes you will, and you add up the moles on each side and they're equal? Okay, what happens in that situation? And you will have some situations where that is the case. Okay, simple answer to that is pressure has no effect. Okay, so you may want to make sure that you make a note of that there are some scenarios where pressure has no effect. All right, let's go ahead and move on to our last concept here. And again, we're using the same equation. Now, this one is a little bit harder to grasp. So we've talked about concentration, we've talked about pressure, and now we're going to talk about temperature as the third factor that can affect or disturb equilibrium, which makes sense because temperature and concentration, we both dealt with rates of chemical reactions, and they can change rates. Now, how does temperature affect or how does it disturb? Well, the first thing you have to know, and you may want to jot this down, is the reaction endothermic or exothermic? And you would have to be told this in the problem. Okay, so this wouldn't be something that you'd look at the equation and have to guess at it. You would be told this. Now let's assume that it's exothermic. Okay, for the most, since most reactions are. And I believe this particular equation is exothermic. Now here's a question that we need to deal with. Okay, if it's exothermic, what does that mean? Well, it means that it's releasing energy or giving off energy, usually in the form of heat. So, okay, if it's giving it off, if I was to insert that into the chemical equation, if it's giving it off, where would I put that in my chemical equation? Well, I would put it on the product side because it's what's produced as a result of the reaction. Okay, so if I wanted to write it as part of the chemical equation, I could put plus heat. Okay, and I'm just going to write H for heat here. Okay, I'm not going to spell the whole thing out. So we'll just understand that H is heat. So what we're saying here is if it's an exothermic reaction, then heat, in essence, is going to be, or temperature is going to be a product. Okay, so now here's the thing. If I increase the temperature on an exothermic reaction, what am I adding? I'm adding more of a product. Okay, in essence, I'm putting more of this right here in. Well, what happens if I put more of a product? Kind of similar to what we were talking about with concentration. If I add more of a product, what are you going to end up with? More collisions on the product side, okay? And as a result, which direction is that going to push the reaction? It's going to push it in reverse. Okay, so that's how that works. Now, if I lowered the temperature, then it would be as if I'm decreasing the amount of a product, and as a result, then it would do the opposite. It would push it in the forward direction. Now, let's go ahead and cross this out here. Let's say it's an endothermic reaction, which means heat is absorbed. Okay, and so that would mean that heat, in essence, is a reactant, and so we would write our H on this side. And so now if I increase my temperature, in essence, I'm increasing a reactant. Again, this is an endothermic reaction. And so if I'm increasing my reactant, then that's going to cause more collisions on the reactant side and push it in the forward direction. Okay, and the opposite is, of course, is true. If I lower my temperature, then I'm going to have fewer collisions on the reactant side, and it's going to force it in reverse. Okay, so that's how temperature works there. All right, I think we're done with that. And don't forget to take the quiz over the last 2 video sessions.